So let's start now.
Yes, sir.
Okay. So in the last class, which was held offline, so we started discussing about SBM with hard margin. Okay, and for that we have derived the equation for the classifier, considering there are no misclassifications. So let us consider the derivation, and here we will try to find the classifier for binary classification. Okay, so let us consider the binary classification for two-dimensional data x1 and x2. Okay, so here we are having two classes, C1 and C2, and here here the data set is two-dimensional. Okay, so there are two features, x1 and x2, and we have plotted the points which are obtained from class C1 and C2. Okay, and here we can see there are three hyperplanes. Okay, three hyperplanes. So middle of the hyperplane is known as the uh, hyperplane, which is used to classify the two examples which are obtained from class C1 and C2. Okay. Now here you can see that there are only one support vector machine on the margin for class C1. So here you can see. So this is the support vector. So which is on the margin, which is used for class C1, and there are two support vectors on the side of on the region of class C2. So here you can see that the support vectors uh, uh, are on the margin which is used for class C2. Okay, and this is the distance that we want to maximize. Okay, so if we consider the margin which is used for class C1 and the margin which is used for class C2 are maintaining the equal distance from the hyperplane. So this is the hyperplane. Okay, and here we can consider this is also a hyperplane which are actually the margin for classes C1 and C2. Okay, this is also called the hyperplane. This is also called the hyperplane. So can you tell me what will be the equation for hyperplane? What will be the equation for hyperplane? So for the equation for the hyperplane, if we consider this is wx plus b equals to 0. Okay, so our assumptions our assumptions that we make for the hyperplane is that the hyperplane will maintain the equal distance from support vectors which are on the margin for class C1 and C2. Okay, so these two are the margins. Okay, these two are the margins for class C1 and C2. Now the equation of the hyperplane will be wx plus b equals to 0. So this hyperplane is in the neutral position. Neutral position means this hyperplane is maintaining the equal distance from margin of class C1 and margin of class C2. Okay. Now, what will be the equation for if we have the class information plus 1 and minus 1? Okay. So yi belongs to either positive class or negative class, plus 1 or minus 1. Okay, so in this situation, so we can have the equations for the margin wx plus b equals to 1 for the margin which is used for class C1. Okay, and we can have the equation for the margin for class C2 becomes wx plus b equals to minus 1. Okay, wx plus b equals to minus 1. Now we can design a classifier for the positive examples by associating the class information yi. Okay, so in this case we can have, so we can write w x plus b greater than equals to plus 1. Okay, when x, let's say this is xi belongs to class C1. Okay, and for the examples which are being classified or which are being obtained from class C2, so for those examples we can have the classifier equation wxi plus b less than equals to 1. So when xi belongs to class C2. Okay, now we can combine both these classifiers which are used for class C1 and C2, and we can associate the class information yi to obtain the constraint. So we can write yi into wxi plus b greater than equals to plus 1. Why? When we combine these two equations which are used as the classifier for class C1 and C2, then we get this constant. So this we call the constant. Okay, so in this constant we are combining both the classifiers which are used for class C1 and C2 by associating with the class information yi. So here we can have yi into wxi plus b greater than equals to plus 1. Why? So every time whatever the class information, so this constant will be found to be greater than equals to plus 1. That means this constant will be found to be always positive. Okay, so if we verify for the negative class or positive class, then we will see that if we consider the positive class, then yi is positive, wxi plus b is also positive. So therefore the yi into wxi plus b will be found to be greater than equals to positive. Okay, if we consider the negative class, that is C2, then we can see that yi is negative, wxi plus b is also negative. So therefore, when we associate the class information with wxi plus b, then uh, we will also get the constant is found to be positive. Okay. Now we will use this constant uh, to design the classifier, and when the training will be performed, we will estimate the weight and bias so that we can use those weight and bias for the unknown samples. Okay. Now for class C1, so we can have the distance wx plus b divided by w. So this is the, we are taking the norm of w. Okay. So this is the distance, this is the distance between the point xi and the hyperplane. Okay. So when we consider, so okay, so in place of b we can write alpha. Okay. This is for class. So when xi belongs to class C1. Okay. So this is the distance, the distance between the point xi and the hyperplane. Okay. And what is alpha here? So alpha, here alpha is the distance between point xi and the margin which is used for class C1. Okay. Similarly, we can consider for class C2 or negative class. So we can write wxi plus beta divided by norm of w. Okay. So this distance we obtain for the negative class C2, where beta is the distance between point xi and the margin which is used for class C2. So here xi belongs to, so when xi belongs to class C2 or negative class, then we obtain this distance. So here we can write this is di, this is okay, d1. Okay. And this is our d2. Now what will be the so this is the distance. If we see it again, then we can see that so this distance, if we consider any point in class C1, then we can see that this is the hyperplane. So any if we consider any point in class C1, so from that point we can consider the distance to the hyperplane, and this distance is given by d1. Okay. So d1 equals to wxy plus alpha divided by norm of w. Okay. When xi belongs to class C1 or positive class. Now if we consider any point in class C2, then we can have this distance. So distance between any point in class C2 to distance between any point in class C2 and the hyperplane. Okay. This is our hyperplane H. So this distance is specified by D2, where D2 is wxi plus beta divided by norm of w. Now what is alpha here? So alpha here, if we consider the point here P1, okay, so this is the distance. So distance between any point in class C1 and the margin which is used for class C1. Okay. Similarly, we can have, if we take any point P2 in class C2, then the distance between point P2 and the margin which is used for class C2 is specified by beta. Okay. So therefore, here D1 and D2, D1 and D2 give the distance between the feature vector and the hyperplane. Okay. Now our objective is to maximize this distance. So our objective is to maximize the distance between two margins. Okay, this is the distance between two margins, and this is our hyperplane. The halfway straight line is the hyperplane between these two margins. Okay, which are used for class C1 and C2. So if we consider the hyperplane is maintaining the equal maintaining the equal distance from each of the margin which are used for class C1 and C2, then we can get the distance between two margins. So if I say this is our D, the distance between two margins for class C1 and C2, then we can obtain Wxi plus alpha divided by plus what we will get minus. Why minus? Because why minus? Can you tell me why we are considering the distance of any point from the hyperplane is found to be negative? Because this is the negative class and the equation of the margin is Wxi plus b minus 1.
So the distance will actually come in negative. So if you do minus, it will be positive.
Yes. Okay. So basically we are trying to sum up these two distances, which are two distances of the feature vector of the points of class C1 and C2. Okay. So basically we are trying to sum up these two distances, and here we will get Wxi alpha minus Wxi minus, oh sorry, this is beta. Okay, beta. Okay, so this Wxi get cancelled. So what is remaining? Remaining is alpha minus beta divided by W. Okay, so now let us consider alpha equals to b plus 1 and beta equals to b minus 1. Okay, now what will be d? So d becomes b plus 1 minus b plus 1 divided by w. B gets cancelled, so 2 by w. Okay, 2 by w. So now our objective is to minimize this w so that we can maximize the distance between two margins which are used for class C1 and C2. Okay, so this is the first objective that we have to attain. So to minimize the w, we have to obtain the gradient. So if we want to minimize the w, so our objective function becomes, so we can write d, okay, say d equals to w square, half of w square. So half of w square we can write w transpose w. Okay, w transpose w. So in this we will make it 0. Okay, so when we will obtain the gradient, so we will make this equation half of w t into w equals to 0. Okay, but when we get this equation to be minimized, then w will be found to be 0, but this is not a desired. Okay, so this to be minimized subject to some constant. So what was our constant? So constant was the yi into wxi plus b greater than equals to plus 1. So this was our constant that we have derived. This is our constant. So this is our constant. Okay, so this we have obtained after combining the two classifiers which are used for positive class and negative class. Okay, now you will say that half of w is to be minimized subject to this constant. Okay, subject to this constant. So we can write yi wxi plus b minus 1 greater than equals to 0. Okay, so now, so initially it was a primal problem. Now we have to deal with the dual problem. That means initially it was a constant optimization problem. Now after considering this constraint, our optimization function becomes unconstant optimization problem. Okay, initially it was a primal optimization problem. After considering this constant, so since we are minimizing this w subject to this constraint, so therefore we are transforming the constant optimization problem into unconstant optimization problem. Or other way we can say that initially we deal with the primal problem or primal optimization problem. So when we transform the primal optimization problem into dual optimization problem, then we have to minimize the w subject to this constant yi into wxi plus b minus 1 greater than equals to 0. Okay, so in this constant here we can see here w is the weight vector, b is the bias. Okay, so bias, so here we have to maximize the bias and minimize the w. So therefore we can write, so now we have to minimize the w and maximize the bias. Okay, so dual optimization problem. So in this dual optimization problem, to solve this dual optimization problem, we will take help of the Lagrangian. Okay, so Lagrangian multiplier will give us the Lagrangian equation. So Lagrangian, we can use this Lagrangian multiplier to achieve this optimization by minimizing w and maximizing bias b. So here we can write L of wb equals to half of w transpose w minus summation, so I equals to 1 to m. So if we consider there are m number of examples, here we are introducing alpha I. Okay, here we are introducing alpha I. So this alpha I is nothing but Lagrange multiplier. Lagrange multiplier. Okay, and this equation is known as Lagrangian Lagrangian equation. So this Lagrangian equation is used to minimize the W and maximize the bias. So after considering these constants, so we can write summation over alpha I. This alpha is Lagrange multiplier into yi wxi plus b minus 1. Okay, so this is the Lagrangian equation. So this Lagrangian equation will be used to optimize W and B. Okay. Optimize means here we need to estimate the weight vector and the bias, so that we can use use both these parameters W and B for classification of the unknown examples. Okay. So unknown examples will not having any class information. So this optimization will be achieved to estimate the weight vector and bias, so that we can use this weight vector and bias in the classifier for the unknown sample or unknown examples. Okay. So in the last offline class, so we have solved this, and so this optimization will be achieved by obtaining the derivative. So obtaining the derivative with respect to W and B. So if we obtain the derivative of this Lagrangian equation with respect to, let us dl, so dl db. Okay. So what will dl by db? So dl by db, when we solve this, when we obtain the derivative dl by db, then we can have dl by db equals to minus summation over alpha I and yi. So you will obtain this. Okay. And we can write, so this to be equals to 1, this to be equals to 0. So we can write summation over alpha I yi equals to 0. Okay. So when we take the derivative of this Lagrangian equation with respect to bias b, then we obtain summation over alpha yi equals to 0. Okay. And when we take the derivative of this Lagrangian equation with respect to W, so what we obtain? We will obtain W minus summation over alpha I yi xi equals to 0. Okay. And this will give us W equals to summation over I equals to 1 to m alpha I yi xi. So here we have determined the weight vector. Okay. Weight vector. Now if you can remember the Lagrangian equation, where we obtain this expanded okay, we obtain this expanded form alpha I, so summation over alpha I yi b, this is bias, minus alpha I yi w xi. Okay. Plus this is the expanded form of the Lagrangian equation, plus summation over alpha I. Okay. So in this equation we will put the W that has been determined. Okay. So after taking the derivative of Lagrangian equation with respect to W. So if we put the value of w in this expanded form of Lagrangian equation, so what we will obtain? We will obtain L of w comma b equals to summation over alpha I, here I equals to 1 to m, minus half of, so it is your duty to solve this equation. Okay, so after putting the value of w in this expanded form of Lagrangian equation, so you will get this, you will get this derivation where we are having two different vectors xi and xj. So here we can write half of, so summation over alpha I minus half of summation over alpha I alpha j yi yj into xi dot xj. Okay, so if we consider this, let me mark so that you will understand. If you consider this, so half of wtw, so in this in this term, if you put the value of w which has been determined in the earlier derivation, then you can have this alpha I alpha j yi yj and xi xj. Okay, now here alpha I greater than equals to 0. Okay, here alpha I greater than equals to 0, and what we have obtained when we take the derivative of Lagrangian equation with respect to b, so here we obtain summation over alpha I yi equals to 0. Okay, so after considering these two conditions, alpha I greater than equals to 0, so here alpha is the Lagrange multiplier. Okay, and we can consider this summation over alpha y equals to 0, this is another constant. So after considering both this, so we can have this Lagrangian equation summation over alpha I minus half of summation over alpha I alpha j yi yj into xi xj. Okay, so now we will design the classifier for unknown sample after estimating the weight factor and bias. If we consider the classifier is f, so we can write f of x cap. So sign of, we can write j of 1 to m alpha j yj xj dot x cap plus b. Oh, sorry. So after estimating the weight vector and bias, we can use the weight vector and bias in the classifier for classifying the unknown sample x cap. So for this unknown sample x cap or the feature vector x cap, we can design this classifier f. So we can write f of x cap equals to sine of summation over alpha j yj xj, xj. So xj is making dot product with x cap plus bias. Okay, so alpha j is known, yj is known. Okay, so this alpha j, yj, xj, so these are used during training. Okay, so basically this is nothing but w. So w is known to us, bias is known to us. Okay, so what is unknown? What is the remaining? Remaining is x cap. So in place of w, what we can write? We can write summation over alpha j, yj, xj. So these three components are known. So alpha j is known, yj is known, xj is known, and what is unknown? X cap is unknown. Okay, so in place of w, we can write alpha j, yj, xj, and this xj will will make the dot product with x cap. Okay, so here we can write summation over alpha j, yj, xj dot x cap plus bias. So we have estimated w. Now how to estimate the bias? So we can write half of b equals to, this b denotes the bias, so half of alpha I yi xi xj. Okay, plus we can write max of alpha I yi xi xj. So when I, so here yi, when we consider the negative class. So what we are writing? We are writing b equals to half of minimum of summation over alpha yi xi xj. Okay, when we consider class level from positive examples. Okay, and then this we are uh, we are taking the summation of this yi alpha yi xi xj when we are considering positive class and negative class. For the positive class, we are determining the minimum of this summation over alpha I yi xi xj. Okay, and we are determining the maximum over the summation alpha I yi xi xj when yi equals to -1. Okay, so when the weight vector w and bias both are given for the known examples during training, then we can use both these parameters. These are also called the model parameters w and b for the unknown sample to classify one of the two classes. If we deal with the binary class, then for the hard margin we can estimate the class information of some unknown sample after having weight vector w and bias from the training process. Okay. Now we could have another problem. Another problem means when we allow the misclassification. So in that case, the support vector machine, we will consider the support vector machine with soft margin. In the last discussion, we have considered SVM with hard margin, where we do not allow the misclassification, but now we will allow the misclassifications and we will obtain the classifier equation So that will help us to that will help us to classify the unknown samples. So now we are considering SVM with soft margin. Okay. So let me draw this graphical representation. Then we will make you understand how we can obtain the support vector machine classifier with soft margin. Okay. This is our C1 class. This is C2 class. This is one support vector. This is two support vector. So this is the equation of hyperplane. This is the equation of margin for class C1. Okay, and this is the equation for the margin for negative class or class C2. Okay. Now let us consider there is an example from negative class which is appeared on the region of the positive class. Let's say here we have obtained one examples from class C2 in the region of class C1. Okay, and we can have another examples from negative class or from class C2 in between the margin of class C1 and the hyperplane. Okay, and we can have other examples from class C1 which are found in the region of class C2. Let's say this is one example and this is another examples from class C1 which is found in between the hyperplane and the margin of class C2. Okay. Now how to deal with this when we allow the misclassifications? Then how to design the SVM classifier after considering this misclassification from class C1 and C2. Okay. So, so that means if we consider the misclassified examples of class C2, then we can have this distance. So we have to calculate the distance from the misclassified examples to the margins of class C1, C2. So in this case, there are two examples, misclassified examples of class C2. So therefore, we will obtain the distance from these examples to the margin of class C2. Similarly, we will obtain the distance from the misclassified examples of class C1 to the margin of class C1. Okay. So what do we call this? What do we call this distance? What do we call this? When we when we allow these misclassifications to obtain the support vector machine classifier, then we have to obtain the loss function. So loss function for what? Loss function for the misclassified examples. Okay. So in this case, when we obtain the penalty or the loss for the misclassified examples, then we call this loss of misclassified point as slack variable. Okay, what we call the slack variable. Okay, and this will be added to the both primal problem as well as the dual problem. Okay, so when we add this to the primal problem, then we can write half of w square plus c into summation over I equals to 1 to m. This is called chi. Okay, so this symbol is called chi. So c into summation over this chi I. Okay, so here we are considering this slag variable for m number of examples. So this is called the slag variable. This is called the slag variable. Okay, so this penalty of the misclassified examples from their respective margins for class C1, C2 are called slag variables. Okay, so now we are considering this slag variable chi I for m number of examples. So here we have to, so initially we initially we are trying to maximize the distance between two margins of class C1 and C2 by maximizing the bias of the bias between the examples of class C1 and C2 from hyperplane. Okay, so now we are adding this slag variable for the misclassified examples, and we are obtaining the primal optimization problem as half of w square plus c into summation over chi I. Okay, now what is, so here chi I is the slag variable. What is c? So c is known as the regularization parameter. Regularization parameter. Okay, so this regularization parameter C controls the trade-off between maximizing the margin and minimizing the loss. So when we maximize the distance or the margin between margin between C1 and C2, then at the same time we need to minimize the loss due to the misclassified examples. Okay, due to the misclassified examples. So now this W to be minimized subject to the constant. So what is the constant? So we have obtained the constant when we combine the classifiers for positive class and negative class. Okay. So similar to the hard margin, in case of soft margin, we will obtain the same constant after considering the slag variable. So we can write Wi into yi into wxi plus b. So here we are now writing, so 1 minus chi I. Okay, so yi into wxi plus b greater than equals to 1 minus this chi I. Okay, so when we will obtain the Lagrangian equation, so we will write this primal optimization problem half of w square plus c into summation over chi I minus we will write summation over alpha I summation over alpha I yi into wxi plus b minus 1 minus chi I. Okay, so only addition in the Lagrange equation is the slag variable. Okay, chi I. So this slag variable will be added to this Lagrangian equation, and remaining things will be same with remaining things will be same as that of hard margin. Okay, any questions from today's class? If you have any questions, you can ask me. Otherwise, we will stop now. Okay, that's all for today.